Okay, welcome to another interesting lecture, and we've got another interesting topic as always. Today it's about constraint satisfaction problems and a lot of problems that you see in AI, a lot of real life problems, real life examples are all nothing but constraint satisfaction problems. So the university has a timetable to follow. And what is that timetable? It's a constraint satisfaction problem. All you need to do is to assign courses to time slots to every batch such that the credit hours are intact. No student has to do two courses at the same time. No instructor has to do two courses at the same time, as well as the fact there are no two batches waiting outside a room. As per the timetable, it's ours. So as long as you satisfy that, anything and everything is a valid solution. So if you're looking at it from the perspective of search, of course, it's the major unit of search going on in AI. It's a weird problem. So I need to search, but what I need to search what the goal looks like. Which path do I take to the goal? Do I take the optimal path to the goal? Do I take in the best way out to reach the goal? It just doesn't matter. All that matters is which is that one state which satisfies the goal criterion. That's all. In fact, if you're watching this video at your leisure time, which most probably most of you would be, how did you plan this out? It's a constraint satisfaction problem. There are activities. Some activities follow the other activities. Like only after you watch this lecture can you attempt the assignment. Only after you solve the assignments will your parents allow you to watch television. Okay, you are grown-ups. Bad example. You get meals at fixed timings. Yes, you could make it a little here there, but there are constraints. So you're scheduling a number of activities as long as all job is done the end of the day, whatever as per your plan. It absolutely doesn't matter how did you create a plan. The final thing has to be constraint free, not you doing two things at the same time. Planning a holiday is also what is constraint satisfaction problem. You need to be sightseeing interesting places. Wonderful. Yes, you could be adaptive on meals here, but there are certain things which you might want to visit before the others, the major spots before the others, as well as the fact that the day you depart and the day you arrive, they act as some kind of constraints. The timings are a constraint. Museums are not open round the clock. They are timings. So is the beautiful sunset. It happens at a specific time. If you want to watch that, follow the constraints. Anything as long as you look at everything is what is a valid solution. The classic example are, of course, the n queens problem. So you need to place all the queens on a board such that no two queens cut each other. The Sudoku arranged numbers 1 to 9 on a 9 cross 9 board, no numbers being repeated in row or column or in a 3 cross 3 section subboard. There's also a constraint satisfaction problem. So today what we're going to do is we study this constraint satisfaction problem, and normally I'm the one who's more excited on constraint satisfaction because the solvers for constraint satisfaction problems, or CSP as we know it, are now so advanced that virtually every problem we're trying to see, okay, can we solve it by CSP? The last you would have heard the statement, would probably be for machine learning. Everybody's trying to see, can I make a machine learning problem out of it because the solver is beautiful? CSP solvers now can solve in a humongous number of constraints very easily and give you a solution. Of course, we'll not be going into that depth. This course will be more or less on the basics of it. Now, before we really go upon, let me give you a few definitions as always. So I've got something which is called as a variable. So finally, my problem is represented as a set of variables till last we call as state variables that encode my problem, and all that I have to do is to assign values to these variables such that each one of the values is from a known domain. So let's quickly take an example. N queens, 8 queens, and let us say I know each one of them needs to be placed in a separate column. So the row numbers is all that I need to decide. So my variables are in which row should be the queen corresponding to the first column, which row should be the queen corresponding to the second column, ith column, and similarly the row at which the last queen, which consists of the queen number at column 8, where should it be placed, at which row number. Now, the domain of any variable, in this case, luckily, I can just say v of I because all variables have exactly the same domain. It will not always be possible. Are from a set 1, 2, 3 all the way up to 8. So finally, the thing that I need to do is I need to make an assignment of values to these variables such that values are taken up from this domain. So I say v1 is equal to 1, v2 is equal to 6, v3 is equal to 2. So these are assignments, and that's all that I do. I just take in values from the domains, I assign it to my variables, and that's how I solve the problem. But then, of course, you have what is called as constraints. And constraints are the ones which make my life a lot more harder, because if you take in just 2 variables, you will see it's not that easy. So that's my n cross n board. And this is my columns. So that's my variable v1, v2, v3. And let's just take 2 variables v1, v2. I cannot place a queen here. So there's a constraint. The constraint will be defined by, of course, the list of variables that participate in that constraint and the relation which stands for the constraint itself. So if you want to take an example over here, v1, v2 have a constraint that the value of v1 cannot be value of v2, otherwise the 2 queens will cut each other. There are more constraints, of course. There is a more subtle relation that they share to each other. It turns out even that's a invalid solution. And why is it a valid solution? Invalid solution because the queens are still cutting each other. So it turns out that v2 minus v1 cannot be equal to 1. Otherwise, the 2 queens will cut each other. And of course, I mean, it's a little bit more subtle that even this is not a great solution because the 2 queens are cutting each other. So lots of constraints, and you can do it for all queens. So v1 has a constraint on v2, v1 has a constraint on v3, v1 has a constraint on v4. God, every 2 pair of queens have a constraint on each other. And constraints are why my life is a little bit hard. I need to do only assignments which are valid, or said, which are consistent. So a consistent assignment means that starting from nothing, all the values that I assign to variables will be such that none of the existing rules is broken, none of the existing constraint is violated. So I'll only do a consistent assignment, and once I do a consistent assignment, I get what is called as a partial solution. So some variables have values, some others do not have values. And once all variables get their values, I get it as a total assignment, which is my solution. So after you've assigned values to all the variables, you've got your results, you could terminate out over there, you've done what had to be done. Now the golden word, of course, here is, what is a constraint? So let's look at it a little bit more deeper. So in reality, you'll get in multiple kinds of constraints. So let's say you've got a constraint which is given by v1 plus 10v2 plus 3v3 is equal to 0. That is what is an equality constraint. On the other hand, you could also have an inequality constraint, which is 10v1 plus 3v2 is less than equal to 5. That's a linear constraint. You could have nonlinear constraint. So a nonlinear constraint is 10v1 plus 5v1v2 plus 3 times v2 square is plus 5 is less than equal to 0. It's a nonlinear constraint. You've got quadratic terms around over here. It could have other terms as well. So there are many types of constraint. However, we are doing classic AI, and therefore I'll make this problem as simple as possible by applying some kind of an assumption. So my assumption is that I only have problems which are discrete domain. So I cannot have 1.3, 2.9. Why that? Because if you want to go into non-discrete domain, there are other courses. They talk beautifully about it. As well as my domain will be finite. So I'll always say that I've got a finite set of elements to choose from in the domain, and that makes my life a lot easier. I'll also not consider other kind of constraints which are called as the preferentiality constraint. Now, there's a reason why we do not consider preferentiality constraints, because preferentiality constraint is, in the timetable, if I get a 9 o'clock class, I'm like, oh God, I don't want to take it. Course allocation is another constraint satisfaction problem, and there are some courses, let me not name them, taken last semester. I'm seriously like, do I need to really take it? I'm not happy about it. So the preferentiality constraints, they rely on what's called as a preference. And we'll not be looking into it because preference leads to some solutions being more preferred to the other, or the added notion of optimality. And remember, it's a lot of variables, lot of domains, big fat domains. So yes, you could solve this problem by classic search. It'll take a humongous amount of time. So there are some modern soft computing methods. There are optimization methods which deal with the problem about setting this optimality while not violating these constraints. Now remember, these are hard constraints. I cannot teach two courses at the same time, no matter what. It's just not possible. It's an invalid solution. These are soft constraints. They are not preferred. I don't like morning classes, but the solution will still be valid. It will not be optimal, but the solution will be valid. So the head of the department will say, yes, it's not best for you, but you have to do it. So under these assumptions, I will start off the exercise in order to really make in a solution that solves the problem of constraint satisfaction problem. And therefore, let me just take in a synthetic problem, the most widely used as well. So there's a nice drawing that I have over here in 2 pages, and the drawing has some sections like this. So let's name the sections as A, B, C, D, E, and F. All that I have to do is that I need to color these sections by some color out of the colors which are available to me. And while doing so, no two neighbors should have the same colors, because if I color this as red and this also as red, I won't be able to see the boundary. It'll not look good. Arts people know it. So I need to color them up by different colors. So my variables are A, B, C, D, E, F, and the domain of any variable Vi is, let's say I have 3 colors, RGB. I'm only given these 3 colors to choose from. And my task is to color each one of these things up. So constraints are that 2 neighbors cannot have the same color. So A cannot have the same color as B. A also cannot have the same color as C. A also cannot have the same color as D. Also, D cannot have the same color as E. C also cannot have the same color as D. B cannot have the same color as D. Okay, I'll not write down all of them, but no 2 neighbors can in this problem have the same color. So let's start coloring and let's see how does it go. And each one of these is an assignment. So I first make an assignment of A is equal to red. I like red. It's also the color that I chose. So I color A as red. Now I need to do an assignment, let's say for B. It cannot be red, so I say B is equal to green. So this gets green. Let's do another assignment. Let's say C. I like green, so C could be green. So this becomes green. D, it cannot be red, it cannot be green, so let that be blue. And E, it cannot be green, it cannot be blue, so it could be only red. F, my favorite, red. I like red. So, we've got the solution, hooray. And we've got it pretty easily. And the only thing that I need to do is, of course, to now make in a computer program that does this little thing. Now, let's look at what are the type of constraints that I am dealing with, which will be a general constraint for any constraint satisfaction problem under the discrete finite domain assumption. So you're going to have a unary constraint, And a unary constraint, it just says a certain variable cannot take in a certain values. So like I said, I love A, it's the largest in the picture. I love this thing at A, and I hate green, already said. I also hate blue. So I have a unary constraint, A cannot be green or blue. Now what the unary constraint really does is the domain of A was previously R, G and B. G is gone, B is gone. So now the domain of A could only and only be red. So that's an indirectly saying I want red. So the unary constraints are therefore constraints on a single variable over here, and they are easiest to handle. Just delete out illegal values from the domains. That's the only thing that you need to do. We also have what are the binary constraints. You looked into a lot of them. So a binary constraint is a constraint on two values. So A cannot be B, or V1 plus V2 cannot be 5, or V1 minus V2 cannot be plus minus 1. These are all binary constraints. It's a constraint between two variables. So most of the constraints that we've looked at were binary constraints. We also have a higher order constraint. Give it any name. I'll call it as the global constraints. So these are constraints between more than two variables, 3 variables, 4 variables, 5 variables. Unfortunately, that example, there wasn't a real global constraint. So let me make it a problem. So let's take the crypt arithmetic problem. 2 plus 2 is equal to FOUR. You need to assign values to T, W, O, R, U, F. All of them different from domain 1 to 9, 0 to 9, and the addition should happen correct. So you got O plus O is equal to R, but there's an invisible carry forward, C1. W plus W plus C1 is equal to U, but there's an invisible carry forward, C2. So you have O plus O is equal to 10 times C1 plus R. Okay, now this is O and this is 0. So that's a constraint between O, C1 and R. Now we'll not be dealing with these constraints as well. There's another constraint that all of them need to be different. T, W, O, F, U, R. All of them need to be different. So it's a constraint between all the variables. All of them need to be different. We'll not look at tertiary higher order constraints for a reason. And the reason is that I can always reduce a higher order constraint into something else. So let C1 and R be just one variable, and let's call the variable as alpha. So now the constraint is only between O and alpha, where alpha internally has a C1 and R, so I can still refer to the variables. All that I need to do is the domain of C1 was 0 all the way up to 9. The domain of R was 0 all the way up to 9. The domain of the new variable alpha can be any valid assignment. They cannot take 0, 0 because it's all different. So 0, 1, 0, 2, 0, 3, 0, 9, 1, 0, 1, 2, all the way up to say 9, 8. That's the domain of the value alpha, and I still have access to both the variables. That's possible. Now, let's have a generic representation in case the original problem appeared to be something which is too specific. So now remember, I only have binary constraints. Anything which is a non-binary constraint has been decomposed into a binary constraint. So I say that the problem is modeled as a graph where all the variables are vertices. So A, B, C, D, E, F are vertices, and two variables which have a binary constraint between them, binary constraint, have an edge. So AB has a constraint, AC has a constraint, CD has a constraint, AD has a constraint, BD has a constraint, DE has a constraint, BE has a constraint. Simple enough. All these variables, all these pair of variables, they have a constraint. It becomes interesting if I actually had higher order constraint, where again, let's do it only for these variables, which is O, C1, and R. So instead of constraint graph, I'll have a hyper constraint graph and a hyper edge, which is noted like this: a constraint between O, C1, and R. And that's exactly what we did. We tried to combine these up into a normal binary constraint. So this is what is currently a hypergraph. And my problem is to reduce a hypergraph with higher order constraints into a normal graph with only binary constraint using auxiliary variables. Another way you could do that is, of course, every constraint has a number. So let us say this is the constraint cons 1, and similarly there are other constraints 2, 3, 4, and they all have some participating variables. So how do you reduce a hypergraph to a graph? Take every constraint as a variable, and any two constraints, variables, sharing variable is an edge. So cons 1 becomes a vertex, you'll have cons 2 as another vertex. If they have a constraint in common or variable in common, say R, so I'll draw an edge from cons 1 to cons 2 and you get another graph. Now, luckily, we won't be looking at these issues about the reductionism of higher order constraints into a lower constraint. Most generally, I will be, in the rest of the lecture, working on this as a constraint graph. And I'll see that, okay, how do I go about solving in a constraint graph which is given to me in this kind of an order and in this kind of a fashion.